There you go. You can write that down. You got that? Yeah. Oh my goodness. Right. Continue. I'm tired too.
Take a break.
No, we'll be strong. Have you got class after this?
Yeah, chemistry.
I don't. We'll keep going until we run out of energy, okay? So if we get too tired, we can make this 2 lessons, alright? Okay. Because the mass of a proton and a neutron are so small, we don't use kilograms. I mean, we could use kilograms, and we have used kilograms, but we use a smaller unit called the AMU, atomic mass unit. The symbol is just U or AMU, okay? And the definition is 1 AMU is this much kilograms. So it's used to measure a very small amount of mass.
We have to write all the decimal.
I don't know. Let's see. In the exam, they give it to, I don't know. I'll just write the whole thing down. It's not going to kill you. It's on your calculator. It might just be called U. Yeah? You got that? Yeah? Now, the reason we use this unit is because it means that 1 proton and 1 neutron, they're both roughly 1 AMU. So it's a good unit to use for measuring the mass of protons and neutrons and atoms. So, for example, the mass of 1 proton or neutron is about 1 AMU. Okay, do you have that? Yeah? Now, let's look at the following nuclear reactions. Very simple nuclear reaction. You have, what is this element? Hydrogen. How many protons? How many neutrons? No. 0 here. This one? Lithium. 1 proton fired at the lithium-7 will make 2 heliums. Now, is this balanced? Well, let's check. Is it balanced? 1 plus 7, does that equal 2 times 4? Looks balanced, okay. 1 plus 3, does that equal 2 times 2? Looks balanced, okay. Seems to be. Now, note the masses, okay. The mass of 1 proton is about 1.007 AMU. 1 proton. The mass of lithium-7 is 7.0016 AMU. And the mass of helium-4 is 4.002 AMU. I want you to add these 2 masses together and tell me what you get. So this is that one plus that one. What do you get? Do you add them together? 8.023 AMU on the left. Did you write that down? 8.023 AMU on the left. Now, on the right, Andex, since you have the calculator handy, could you do 2 multiplied by 4.002? 8.004, yeah. On the right, 8.004 AMU. Now what's the problem here? Which mass is bigger, the left or the right?
Left.
The left. Now that's a problem, isn't it? Because if you have, imagine I told you you had 1 kilogram and 1 kilogram and they came together and you did not get 2 kilograms. What do you think would happen? Something went missing, yeah. But in this reaction there isn't anything missing. Everything is there. There isn't anything missing. So something is happening here that's very strange. You have 2 masses, you put them together, and the result is smaller, a little smaller. Yeah? It's quite strange. Now, what's going on here? Mass does not just disappear, right? Or does it? So, let's see. Is there something missing here? Well, the answer is yes, and the reason is this experiment was done by Cockcroft and Walton about 100 years ago. Now, they didn't wake up one morning and decide to fire protons at lithium, okay? There was a reason why they were doing this. They were testing some paper that Einstein, a young Einstein, had about energy. See, Walton didn't just decide to do this experiment one day. He was trying to test a formula that Einstein had. Einstein predicted that when atoms combine in a nuclear reaction, some of the mass appears to be lost. But it wasn't lost. Instead, it was converted into energy. So when the 2 masses came together and became a smaller mass, what happened was some of the mass was turned into energy. That's what Einstein predicted, that you can turn some of the missing mass into energy. In fact, Einstein had a formula for this, a formula that you all know, E equals mc squared. Or you can write it as just like that if you prefer. The reason we write delta E is because it means extra energy, and delta M meaning lost mass. Yeah? Have you seen this formula before? What? You've never seen this before? Never?
Maybe in the formula book?
Oh, I thought this was famous, like Pythagoras. You've seen it before?
Anything?
Huh? You want me to prove it? I can prove it, but you can't understand it. The proof is about, it's not too long, it's about 2 pages. So it's not too bad. It's not too bad. You will never see the proof because you're doing computer science. You won't see the proof. You won't see the proof. You won't see the proof. Okay, none of you will see the proof. You could always download Einstein's paper and read it if you like. Okay. So Einstein had this formula in his paper about 100 years ago, and Walton wanted to verify this formula. So let's go back to this example now. Andek, what did you say the mass was on the left here? Let me write that down. 8.023 AMU, and on the right was 8.004 AMU. So the mass that appears to be lost is 0.019 AMU. Now, is it really lost? No. Einstein said it was converted into energy. Okay, well, let's see. So the energy should equal mc squared. Now the m is AMUs. What did we say an AMU was at the start, roughly? 1.66 times 10 to the minus 27 times 3 times 10 to the 8 squared. Okay, what's that, please, when you're ready?
Times 10 to the minus 12.
Now, believe it or not, that's a lot of energy when you compare it to the size of the mass. Like, it really is a lot. So, what's happened now is when the hydrogen and the lithium combined, they made 2 helium and some energy. It's actually a lot of energy. It really is. I can show you with a bigger number example. Imagine we have 1 kilogram, and then we were to convert all of that 1 kilogram into 0 kilograms plus energy. Now, please don't be confused. I'm not saying like you can burn it, because when you, like, if I have this piece of wood here and I burn it, we still have 1 kilogram. It's just the 1 kilogram has moved as smoke in the air or on the ground as ash. It's not like I've destroyed the mass. What you're doing here is you're destroying the mass. It no longer exists. It's gone. You start off with 1 kilogram, and then you have 0 kilograms, completely gone. Everything is turned into energy. How much energy would you have here? Well, Einstein said you would have this. What's the m in this example? It's just 1. That's equal to 9 times 10 to the 16, which is roughly 10 to the 17 joules. Now that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 joules. So you take something which is about 1 kilogram, like I don't know, what would be my laptop, you know, about 1 kilogram, whatever, okay? And if you could convert that completely into energy, destroy the mass completely, you would get this much energy. That's a lot of energy. So there's a lot of energy inside of atoms, a lot of energy, waiting to be released. You understand what I'm saying here? Like, it's really a huge number. Okay. So is this example okay? This is a section A question. You know, what is the energy in this equation? Okay. The mass of a proton is 1.00776 AMU. That's 1 proton. The mass of 1 neutron is 1.008665. I would like you to add those two together and tell me what the mass is of... I want you to take 2 of these and 2 of these and add them together. Tell me what the mass is. Oh, it's, yeah, sorry, I just spotted that. It's upside down. So, 2 of these and 2 of these together, please. Okay, 1 sec. Hydrogen 1, 1 plus hydrogen 1, 1 plus neutron 1, 0 plus neutron 1, 0. I'm going to make... what do I have if I have 2 protons? It's taking longer to load. Helium. Okay. Now, what did you say the mass we think should be? What should it be? You have it there on your calculator.
4.031882.
AMU. Okay. That's what it should be, right? If you add these together to make a helium, you should get this. But do we get this? The mass should be 4.031882. It is in fact only 4.002602. 00? No. 00 here. Again, this is a little bit strange, isn't it? You know, if you take proton, proton, these are protons, by the way, neutron, neutron, you stick the four things together, you get helium, but the mass of this helium is less than the four things separated. That's strange. You know, you put four things together, you get less mass. You separate them, you get more mass. It shouldn't be like that, right? If I put two things together, it should be the same mass. Okay. So again, what is happening here? So, I think there's an extra zero here. I don't know. Doesn't matter. So there's some mass that's missing. We call this the mass defect. It's the missing mass. So just to give a definition, I think it should write this down. Mass defect means missing mass. You looked like you were ready to sleep. You got mass defect written down? Okay. You didn't fall asleep in the middle of writing it down. Continue. So the reason this mass defect disappears, let me explain. I don't think you did this in chemistry. So you know, what keeps the proton and the electron stick together? Well, that's easy. If the proton is positive and the electron is negative, then the opposite charge makes them stick together, right? What charge is a neutron? No charge. What charge is a proton? Positive. Why can I stick a proton with a neutron if there's no charge?
There's no attraction.
There's no attraction, so how can they stick together? Or worse, what about a neutron and a neutron? How do they stick together?
They repel.
No, they both have no charge. So how does a neutron and a neutron stick together? You see, you didn't talk about this in chemistry, did you? You don't know. So what happens is, when you stick a proton and a neutron together, they're stuck together. They need some energy to stick together, right? They take this energy from the mass. That mass defect, that was taken by the proton and the neutron into energy to keep them stuck together. So it's like proton, neutron, you stick them together and they decide to use some of their mass to make an energy to keep them stuck together, because they can't naturally stick together, unlike a proton and an electron. So this gives us the idea of what's called the binding energy, the energy used to stick two protons or two neutrons or whatever together. And the binding energy of an atom is the energy required to hold the nucleus together. This energy E, do you want to guess what the formula is for it? Go on, I'll give you one guess. Correct. Where M is the mass defect, that is the loss mass. Oh, Matt, where were you last week? On Friday? Where are you? Were you drinking too? Are you sure? Are you honest?
Yes.
Okay. You said you were tired. Playing video games? Fortnite? League of Legends? Warhammer? Huh? Delta, the first person shooter, is it? Oh, is that
Delta.
role playing game, is it?
It's like
Is it like League of Legends?
Yeah, League of Legends.
You play a lot of Delta? League of Legends?
Before, I think maybe 8 years ago.
Which game?
Dota.
Okay.
Dota 1.
Ah, you're on to Dota 2?
And now I still play League of Legends.
It's a pity you don't study physics as much as League of Legends. Right. Okay, you got that? You got that? So look, this energy that you need to stick the proton with the neutron, that's the same amount of energy you would need to separate them. Okay, so if I have a proton and a neutron stuck together and somebody said, how much energy do I need to pull them apart? That's also equal to the binding energy. Okay, so you know what, we could calculate for this one, although I think I have that coming up as the next example. Yeah, I do. That's the next one. Okay. Right, so in an early lecture, we saw that the weak nuclear force is trying to push apart the nucleus. So you remember we said we have like your uranium. So there's your uranium, and then there's radiation coming off of it. So what happens is the uranium is literally like breaking down. It's falling apart. And we said there must be some force that is pushing it out. And we called that the weak nuclear force. Well, Newton's law tells us that the atom's not decaying, then the net force should be zero. So here's an atom. Take, for example, uranium-238. If some alpha radiation comes off, it means, according to Newton's first law, there must be some force that pushes it out. This force is called the weak nuclear force. Okay? But let's take something stable like carbon-12. That's stable. Okay? You have the weak force pushing it out, but it doesn't decay. It's stable, right? There must be some force pulling it back in to cancel the weak one, and that's called the strong nuclear force. And this is the force that tries to keep the nucleus together. So inside the nucleus there are two forces acting. Okay? There's one force that tries to push it out, and there's another force that tries to pull it in. And these forces are usually balanced, except when you have radiation. Which force is bigger? The weak one is bigger. That's when the atom starts to collapse, fall apart. Okay? So you need to know three things about the strong nuclear force. So guess what the three things are. What's the first one? Even simpler than that. First thing is strong. Okay? That's the first thing you need to know about it. Yeah? Seems reasonable, Siva? Yeah? Next thing, it's an attractive force, which means it's trying to pull the atom together. So first it's strong. It's an attractive force. it acts inside the nucleus of, let's just say, of an atom over a very short range, only 10 to the minus 15 meters. It is the force responsible for keeping protons and neutrons together. You got that? Yeah? Do you talk about binding energy in chemistry or not? Does it come up, binding energy? No? Okay. Continue. Right, so we had this example earlier. Let's calculate the binding energy here. So I think I still have it written down from earlier. Go back up to it. Here it is here. This example from earlier. So according to Einstein, the binding energy would be the missing mass. So what's the difference here?
0.02928.
2928. Now I think I've done something wrong here, but it doesn't matter. I'll take that as it. So that's 0.02928 times 1.66 times 10 to the 27 times 3 times 10 to the 8 squared. Okay. Yes, thank you. It's quite different. Times what?
10 to the minus 12.
Joules. Yeah? It's okay. It's okay. Continue. So the next one, same thing again, but this time I want the binding energy per nucleon. Okay, so this is the energy it needs to keep the whole thing together. If it's bigger, it needs more energy. What we really care about is how much energy it has per nucleon. I'll show you what I mean. So like here, imagine I have two things stuck together, and then there's some energy to keep them stuck together. Okay, and imagine I have four things being stuck together. Which will need more energy? Well, of course the four, wouldn't it? But maybe this four isn't stronger than these two. The only way we can compare is if we look at it per nucleon, you know. So for example, let's just say this is x joules and this is 2x joules. Well, this one is x per 2 of them, and this is 2x per 4 of them, which is the same as x per 2. So that's okay. But if I said this needed 3x, well then it needs much more compared to the original. You're looking a bit confused. No? It's kind of like, you know, if I stick things together, if I stick more things together, then I need more energy. Well, what's really interesting is how much energy do I need on average for each part. So if I have 3 things, I should divide by 3. So likewise, if I have 4 things here, I should divide by 4. So, Andek, if you still have this on the calculator, if you just divide by 4 and you get 1 point, well, yeah? 4.37 divided by 4?
1.095 times 10 to the minus 12.
Okay. That's for each nucleon. That's per nucleon. Yeah? Continue? Continue? So there's only one thing left, which is this graph, and I just need to explain this graph. So on the bottom here, you can't quite see it, but you have the number of nucleons, the A, the mass number, okay? So the first one here, which you can't see, is 1. So of course 1 would just be hydrogen, okay? What's after hydrogen? Helium. So that's helium. And then around about here, by the way, and you need to know this one, around about here at 56, I think it is, we have iron, Fe. Okay. Now, on the y-axis, you have the binding energy per nucleon. Per nucleon. So what this graph is showing you is, as you go across the periodic table, up here, what did we say uranium was? Uranium 238, 239. So up here at the end is like uranium. See, uranium. Okay. This needs less energy to hold it together than some of these atoms. It starts to decrease. So this means uranium is quite easy to separate. Well, sorry. It's easier to separate than, say, like, what's Xe? Zion, is it? What is it? Oh, I don't. What's copper? Cu. So you need less energy than you would for separating copper. So iron is the most difficult element to separate. Okay, if you have an iron nucleus, it's extremely difficult to break that nucleus open. It's, in fact, the hardest thing to break open. The easiest thing here to break open is uranium. So in the exam, they sometimes ask you to draw this. Now, of course, you don't need to have all these numbers here. What they want to see on your graph is that you mark iron as the peak, okay? And that here is the nucleon number, and this is the energy per nucleon, the binding energy per nucleon. Okay. Now, before you write that down, you see the graph is broken in half. Okay. So this region of the graph we call the fission region, and this region we call the fusion region. And we'll actually have a lesson later about these two things. So we'll explain exactly what they mean. But roughly speaking for now, this means it's easy to break it open, and this means it's easy to stick it together, fuse it together. Okay? But we'll talk in more detail later about that. So if you can copy this graph down, including these words.
Take a picture.
I would prefer if you drew it. Roughly, just roughly. Which word? Average binding energy per nucleon. And the unit, Siba, is mega electron volts. She's great hearing but terrible eyesight. It's her weakness.
What's the first word?
This average. And this is number of nucleons in nucleus A.
Energy per
Mega electron volts.
and E.
Mega electron volts, yeah, MeV. Do you draw this, Kim? Do you write the names down? Fusion and fission? You've good eyesight? Yes? You wear contacts? Ah.
Number of nucleon.
Got that?
Yeah.
Yeah.
Wait, no.
How's your coffee, Siva? Do you like it? The flavour? I don't like Starbucks coffee. Do you drink energy drinks? No? I don't like them, but lots of students like them. What? Red Bull, Monster. Not nice. Ah, it tastes pretty bad. Tastes pretty bad. Yeah?
I don't like them.
No. I don't understand how people drink them.
Once drank coffee and Red Bull.
Yeah, I see people do that. They mix the two together.
Yeah.
There's some weirdos out there. Oh, you're drawing this too nicely, Chow. Too nicely.
And this peak is which one?
Fe.
FE.
Oh my.
What's wrong?
She called me weird. Okay. She called me beautiful.
Look, if you're weird, then so is she.
Yeah, she said that.
Yeah,
Hey, something on.
exactly. We're all weird together here. There's no exception.
Was it Mother's Day in City?
Yes, in Ireland. It's different day than in America.
Why was it?
Yeah, the Mother's Day is in
Yeah.
The
May.
reason,
In May.
31st.
well, no, the reason it's different here, I think, because the way it works is in Irish calendar. So you have Easter, you know Easter, of course, and then you have the time before Easter called. You know the name of this time? Pre-Easter. No. Called Lent, okay? And that's 40 days. And Mother's Day here falls usually in the middle, 20 and 20. And the reason for that is it's to do with Mother Church. So the idea is you go back to the church of your, you know, like your hometown church when you were a child, you know. You get the idea. So, whereas I think in the America, it's just, it has no religious meaning. It's just this day. That's it, right? Yeah, no. Do you have Mother's Day back home? So it's probably the same day as in America.
It's on the 21st.
In May.
First Sunday of May.
It's on the 21st.
I think
But that's a different day to the America. Yeah.
America's the 31st.
Ah. So
Yesterday.
did they do that just to be different, was it? Or like, is there any special reason for this day?
Why is it 21st?
Yeah.
I don't
Yeah. It just, they picked the day and it's this day. Okay.
Probably.
Right, okay. Please bring your laptop to the next class. Thank you.
Tomorrow?
Tomorrow then, fine.
Tomorrow?
Whenever the next class is.
Yeah, tomorrow.